Hello. In this video we're going to take a look at spherically symmetric potentials in 3 dimensions. So potentials of the following form. That is, V, which is usually a function of x, y and z, or r, theta and phi, is now only a function of the radial coordinate r. So our time-independent Schrödinger equation in general in 3 dimensions in spherically polar coordinates takes the following form, as we saw in a previous video. So now our potential term is only going to be a function of r, giving us the following. So our time-dependent wave function psi, we know can always be separated into a time-dependent part and a spatially dependent part, where the spatially dependent part, let's write it as this slightly fancier phi, just to distinguish it from the polar coordinate phi. But now, in the case of a spherically symmetric potential, when we have this potential as a function of r only, we can additionally separate the radial part from the angular parts as follows. Defining phi of x is, where x is a 3-dimensional vector, is r of r multiplying y of theta and phi. When we substitute this form back into the time-independent Schrödinger equation up here, we get the following, where the time-dependent part t, of course, we can neglect in this equation, the time-independent equation, and r and y have been substituted in place of phi, but here L squared acts only on y because it only the angular momentum squared operator only cares about theta and phi coordinates, doesn't care about r. And so r has pulled through the L squared, and similarly over here, these derivatives of the radial part act only on r, not on y. So we can divide through by ry to give the following, and then we can multiply through by 2m small r squared to give this result, where the first term here is only a function of r, the second term is only a function of theta and phi, and the third term is again only a function of r. So we now have successfully separated our equation again, where we have the following, if we just rearrange things slightly, and let's get these out of the way for a second, where the term dependent on theta and phi is over here, the terms dependent on r are all over here, and since these must equal each other for all theta, phi and r, they must both be equal to the same constant, which we can define to be h bar squared k squared, where k is some dimensionless number because L has the units of h bar of angular momentum. So we have 2 separate equations that we can work with here. Let's call this one equation 1. This term equals this constant, and equation 2, this whole term equals the same constant. So we'll work with these parts separately. So first let's look at the angular part, equation 1. So our angular equation tells us that the angular momentum squared operator, L squared, acting on y of theta and phi equals h bar squared k squared y of theta and phi. We've seen in a previous video, or you can just work it out, that in angular coordinates, the angular momentum squared operator can be written as follows, just expanding the operator here. If we multiply through this entire equation by sine squared theta, we get the following, where I've also divided through by the h bar squared on both sides. So this y is a function of theta and phi, but actually this equation is once again separable using the following definition. So define y of theta and phi to be a function p of theta multiplying a function f of phi. We insert that into the equation to find, and in the usual way we divide through by pf to get the result, where I've rearranged slightly to get only functions of theta on this side, and so these derivatives again have become total derivatives, and only function of phi on the right hand side. So once again, since these must be equal to each other for all theta and phi, they must both equal to the same constant, which we can define as follows. It's equal to m squared, where this is the conventional choice, but as we've seen in previous videos, m is not the mass now, it's a little bit confusing. It's just some constant we're using to separate these equations. Later on we'll find it turns out to be an integer, but for now it's just some number to be determined, which is not the mass, but unfortunately is usually given the same symbol. So once again we have 2 equations here. Let's call them A and b. So A is that this function of phi is equal to m squared. Equation B is that this function of theta is equal to m squared. And we need to deal with them both separately. So within the angular equation, we're going to move to look at A and B separately. So first, the polar equation A tells us that the second derivative of f with respect to phi squared is equal, so minus that is equal to m squared f of phi. So we can see that the following solution solves this. So f of phi is, technically it's proportional to e to the plus or minus I m phi, but the constant of proportionality won't matter because we've got so many separable equations that we can define our normalization as part of the full solution in a second. So let's just say this is equal for now. This is really a definitional choice. We could put a normalization here and it would change our normalization on the other parts. So this is a convenient choice. And this gives us a condition on the m, the separation constant, because we require that the modulus of f of phi squared is an observable quantity. And so this should be single valued. So for any value of phi, we get a unique value of modulus of f of phi squared. So through a process of reasoning, this leads us to the result that when we vary our polar coordinate phi by a full turn of 2 pi, we should get an exactly equivalent function back in order for this the observable quantity to remain single valued. And if this is true, this places the constraint on m that e to the 2 pi I m must equal 1, and so we have that m must be an integer. And let's box that. So it's important to note that if we take the z projection of the angular momentum as follows, let's just get rid of this bit for a second. So the z projection of angular momentum acting on the state f of phi in spherical polar coordinates is minus ih bar d by d phi, partial, holding r and theta and time constant, acting on phi. But when we look at the form we have here, we see that this simply returns plus or minus h bar m acting on f of phi. And so you see that f of phi is actually the eigenfunction of the Lz operator. And so m here is some quantum number associated with that operator, and it's what we call the magnetic quantum number. So it's convenient to label our wave function solutions f by the integer m, and we'll do that from now on, as m is a good quantum number to describe our solutions. Okay, let's take a look at part B. So B is called the azimuthal equation, referring to the azimuthal coordinate theta. It reads as follows, just copying from a couple of boards ago. It's an ordinary differential equation in terms of theta. And as usual, when we have a complicated ordinary differential equation, the trick is just to look up previous equations and massage this into the correct form. And we can do that in this case. In fact, this is a form of what's called Legendre's equation. And the solutions in this particular case take the following form. We write them as P superscript m subscript L. Superscript m is the same m that we used in the polar equation, and it's a function of cos theta. And these things are called the associated Legendre polynomials, and you can look those up. It's possible to derive this solution, but really all you're doing is massaging this into a form of an equation that was previously studied. So the L here is a new quantum number. It's defined as follows. So in terms of our constant k squared is L plus 1. And again, this choice of how to write things is just really part of the already worked out theory of the associated Legendre polynomials. So this is conventional. And we call this quantum number L either the orbital quantum number or the azimuthal quantum number. And L can take the value of any integer 0 or greater. Because L is an integer greater than or equal to 0. But actually the form of m is now further constrained. Before we saw that m must be an integer, but in fact when we look into the theory of associated Legendre polynomials, we find that the m must be between minus L and L. So let's just box these two. So m and L here are the quantum numbers associated with the squared angular momentum operator. So putting all this back together, we can get the solutions to the angular equation. So recall that our equation was the angular momentum squared operator acting on y of theta and phi is equal to h bar squared k squared y of theta and phi. And we now see that the solutions are these. Y subscript L superscript M of theta and phi, returning the eigenvalues h bar squared L, L plus 1, multiplying the same. And there's a second operator which commutes with L squared, which is Lz, returning the eigenvalues h bar M, multiplying the same. Of course, we could have used x and y, Lx or Ly in place of Lz, but Lz takes the simplest form in spherical polar coordinates, so it's convenient to work with. And in both cases, YLM is defined as PLM of cos theta, the associated Legendre polynomials, multiplying e to the plus or minus im phi, multiplying some normalization, which we'll take a look at in a second. And the result here, YLM of theta and phi, is what is called the spherical harmonics. And these can be looked up, and in general, okay. And again, this is a generally used notation, and you can look up the spherical harmonics and expect to find the particular forms of these functions. Let's just look at this again a little bit in the Ket formalism in Dirac notation. So it's convenient to define our spherical harmonics YLM of theta and phi as the projection into the theta phi position basis of the ket L, M, because L and M are good quantum numbers, so we can label a ket with them at the same time, and that makes sense. So our equations then take the form that we've just seen on the previous board, but written now in Dirac notation. So we have that these eigenstates of L squared and Lz form a complete orthonormal basis. So they're orthonormal. The inner product of L prime M prime with Lm it gives a product of Kronecker deltas as usual, and as usual we can expand this into the position basis into spherical polar coordinates using an insertion of a complete set of states. That is just inserting theta comma phi, this ket, which hopefully it makes sense. It's this ket up here that projects us into the theta phi space, and integrating over theta and phi, but we need to use the correct volume element here, the Jacobian that takes us from Cartesians to spherical polars, so we have a sine theta term here. And so these take the form y L prime M prime of theta and phi starred, because this is now a complex function, multiplying YLM theta phi, integrated over the volume element, and we get these two Kronecker deltas for LL prime and MM prime. So we've shown that YLM, the spherical harmonics, form an orthonormal basis, and in fact additionally they form a complete orthonormal basis, meaning we can write any function of this form. That is, f of theta and phi can be written as a sum from m is minus L to L from 0 to infinity, of YLM theta phi, multiplied by some complex coefficients FLM, to be determined in the usual manner by using the orthonormality of the YLMs. So that's a convenient way to write any function which does not depend on the radial coordinate, only on theta and phi, so things that live on the surfaces of spheres. So that's the angular equation solved. In the next video, we'll take a look at solving the radial equation. Thanks for your time.